My name is Upinder Singh. Today we'll be talking about polynomial hierarchy. The lecture slides have been borrowed from Professor Nabil Mustafa. So we'll be discussing about a new class of complexity called polynomial hierarchy. So one might ask, why then bother studying about a new class of complexity, as we have already covered about so many complexity classes: L, NL, P and P, P space, exponential, and non-deterministic exponential. So there are certain problems um, which we cannot decide whether they belong to NP or co-NP. We'll see in next few slides about those problems. Okay. So in today's lecture we'll formally define polynomial hierarchy using quantifiers, and the next one we'll discuss it using Oracle's Turing machine. Okay. So before we proceed further, let's just look at the definition of NP and co-NP. Okay, so it says a language L is an NP if for any x input x which belongs to sigma star, there exists Turing machine M and a polynomial P such that x belongs to the language if and only if there exists a certificate U which is polynomial size such that the Turing machine accepts it. So for any problem you want to check whether it belongs to NP, you just um, take a polynomial size certificate and check whether the machine accepts or not. Okay, and what is the definition of co-NP? If it's L is in co-NP if L complement is in NP. Okay, so one way to look at the definition of co-NP would be to just like you just take the negation of this statement, this NP. Okay, so that would become x belongs to L complement, either right x belongs to L complement or x doesn't belong to L, if and only if for every u which is of polynomial size, right, such that M rejects it. Somewhat like this. Yes, so x belongs to L if and only if for every u of polynomial size the Turing machine rejects it. Alright, so we take example of independent set. So what is the problem of independent set? So you're given a graph G over the set B and x at E and integer K. So you have the problem where you have to decide, does G have an independent set of size K? So this problem is clearly in NP because you can have a vertex set S of size K and you can quickly verify it whether that vertex set S is independent set or not. The definition of independent set means that your vertex at S shouldn't have an edge between any pair of vertices of that set. Okay, so this problem is in NP. If G has an independent set of size K, this is the certificate for it, and there is a Turing machine M that will verify it. What about the complement of independent set? This is clearly in co-NP, right? Does G have no independent set of size K? Okay, so yeah, the complement of this problem is co-NP. Now, if I give a slightly modified version of this problem, and which is maximal independent set, the word should be maximal instead of maximum because uh, you can have different uh, subsets of vertex which gives the same independent set number, right? So it should be maximal independent set in G. So your given problem is as you are given a graph G and integer K. So you you have to find that is K the maximum independent set in G of size K. What is the maximum independent set of in G? Okay, so the problem here is twofold. Likewise in the previous problem, know you just give a certificate of size K and check whether it is the independent set or not. And you can quickly do that by just checking for all pair of vertices in that vertex set S, which is a subset of your V. You check that whether any pair is, let me just write it down, it will be better I think. So you take S, which will be your subset of V, and you just check your S will be somewhat, the size of this will be this V1, V2, so on till Vk. So you check whether any pair in this Vi, Vk, let me just say Vj, if there is an edge between these two. So if I were to form a Turing machine, how would I go about? I mean, for the NP case I'm talking, first I'll check the given certificate is of size K or not. If it is not of size K, I'll simply reject. If the certificate of size K, what I'll do, for each vertex in the uh, that subset S, that certificate, I'll check every pair of vertex, and if there exists an edge between those, I'll reject. Otherwise, at the end of the loop, I just simply accept. So this is the part, right? But here in maximal independent set, they're asking that is K the maximum independent set? I mean, you have to prove not only that K is is an independent set, you also need to prove that there does not exist an independent set of size greater than K. So is this problem in NP? Any idea? So yeah, as it turns out, it's difficult to frame this problem in, right, this is problem in NP. As it turns out, you cannot find a certificate such that you can quickly verify it. So this problem clearly isn't in NP. What about co-NP? Is this problem in co-NP? Well, the co-NP would be G as a maximum independent set, not K. So you cannot, for this co-NP also, you cannot find out certificate, right? So G belongs to maximum independent set, means independent independent set of size K and no independent size of size K plus 1, I mean greater than K. Why we just need to check for size K plus 1? Why? I mean, there shouldn't be a maximum, means K is the maximal and there shouldn't be an independent set of size greater than K. So we only check for size K plus 1, because the reason being, um, intuitively, like if you check that there is no independent set of size K plus 1, then there cannot be independent set of size K plus 2, K plus 3 for that instance. Like, because any set of size K plus 2 will be having K plus 1 in it, right? K plus those K plus 1 vertex of it, and you have proved for all K plus 1 set of vertices that it is not maximal, that it is not independent set, right? So yeah, the problem is a twofold. So the first part of the problem, that is independent set of size K, as we have seen, it's in NP, right? And no independent set of size K plus 1 is in co-NP. So maximum independent set seems a combination of NP and co-NP problem, right? So yeah, we frame it like formula like this. There exists a small certificate of one kind and no small certificate of another kind. Okay, I'll switch to another note where we can see one more problem in this. So there is one other problem called e-click, which is similar to our independent set problem. E-click is G is a graph in which the largest click is of size k, same as largest independent, right? Even click and independent set, maximum independent set has a one-to-one correspondence. Um, if I'm not wrong, you take the complement of graph uh, and the independent set represents your maximum click. Maximum independent set represents your click. Okay. Yeah. So in this case also you can see that there exists an S which is a subset of vertex such that size of S is equal to K, such that S is a click, and for every S prime which is also subset of V and its size is K plus 1, S prime is not a click, right? So there are two quantifiers in here. That is, one is existential and another one is universal. Another problem called smallest circuit. It says encoded C. C is the smallest circuit computing the required Boolean function. Okay, so and there's what we have to frame, like for every C prime which is of smaller size than C, there exists some input X for which it doesn't compute the original function that we intend to compute. C X is not equal to C prime. So in this problem, you have to compute the minimal function. Likewise, this problem can also be stated in terms of XOR. Likewise, you are given basic logic gates, and you need to form that XOR. As you might be aware that minimum number of NAND, if you have just the NAND gates and you're required to form XOR, you know that 5 NAND gates are required to form XOR. So this is similar kind of a smaller circuit problem that and also more than 5 can also be used, right, to form XOR. So you need to find out the minimum number of AND gates used to form the XOR. This problem is similar to that one. So yeah, the difference being in these two problems is that first, in the second later problem, we have a universal quantifier before the existential one. Okay. Yes. Okay. So here we formally define what we stated earlier. The class, yeah, will be sticking to this notation where let's say there exists U superscript A will denote what that there exists a certificate U whose size is A. Same goes with for every U superscript A means for every U size of U is A. Okay. Yeah. So we here formally define what we mean by sigma 2p. A language L is in sigma 2p if for any input x there exists a Turing machine M and two polynomials p and q. X belongs to the language if and only if there exists a U of polynomial size and V for every V of polynomial size machine accepts it. Okay. So clearly our previous problem was lacking this only. There were two quantifiers. First problem there exists and then universal quantifier. So our previous problem belongs to this class, which is sigma 2p. Okay. So yeah, first part of the certificate U forms the independent set of size k, and the second part, later part V, eh, which is which is used to form the uh, which is used to prove that no certificates of size greater than k exist such that it is independent. Okay, so our Turing machine M verifies that U is an independent set and B is not an independent set. Yeah. So how you go about designing it? How do you find? So how our Turing machine works? So if J belongs to maximum independent set, so K, we are given K, right, and graph G. So if G has a maximum independent set of size K, then our certificate you will accept it, right? Because use an independent set of size K, so you will accept it. Okay. What if G doesn't belong to maximum independent set? Either then in that case, either your K value, your maximum, it will your maximum independent set value will be less than K, right? Or it will be greater than K. Okay. So if your maximum independent set has size less than K, so then in that case you won't be able to find U, right? You won't, the first certificate won't be able to verify it. So if your maximum independent size is greater than K, then one of the V will reject it. Okay. Now this part is clear. Like when it belongs to the maximum independent set of size K, then you will clearly accept it. But if your maximum independent set size has less than K, then this condition, first condition, will be failed, which says that S is an independent set of size K. If it is greater than K, then if it has greater than K, that means U will be passing, because if it has independent set of size say K plus 3, then it also has independent set of size K plus 2, K plus 1 and K also. So you won't be failing there. This part that says S prime is a set of size K plus 1, this part will be failing, because if says maximum independent size, sure, it is greater than K, then not true for all. Okay, fine. So yeah, here we assume two different polynomials P and Q. The condition just requires that P and Q are just polynomials. So in further notation, we'll simply just write P and P for sake of simplicity. Okay, so about the properties of sigma 2P. Here, go to my slides. Okay, here also I've defined it. Yeah, so our sigma 0 and pi 0, sigma 1 and pi 1. So our yeah, sigma 2 was written as their existential. There was a first existential clause, then a universal clause, and then we write P, right? Okay. So sigma 1 would be relaxing the condition on later half, and our pi 1 will be co-NP, that is just using the universal quantifier. We have to prove for all that it doesn't hold, right? Independent set size of K does not exist. There is no independent set of size K for all P. For all independent set of size K, it should reject. So there is a for all P. So pi 1 is equal to for all P, and pi 2 sigma 1 is equal to there exists P. So in a similar fashion, we just extended our concept to pi 2, sigma 2, pi 2, sigma 3, pi 3. Okay, just alternating between these quantifiers. Just remember that when we use a sigma, we start with their existential clause, and when we start with when we're talking about product, we start with the universal quantifier, and then keep on alternating depending on the level. If it's on level 2, you alternate 2 times. If it's on level 3, you alternate 3 times. Okay. So the ith one will be, as you can see from, you can follow from this, uh, pi I will be equal to sigma I, so sorry, summation I will be equal to there exists pi I minus 1. Okay, because this part can be, you can see that sigma I minus 1 would be for every there exists, for every there exists P, right? From the previous level I took it. Similarly, this can be written, right? product of I can be written in terms of summation I minus 1. So yeah, without any constraints, there exists and for all is simply polynomial class, right? And if we restrain and if we apply more, if we apply conditions on it, there exists and for all, it introduces a new class of complexity. Okay. Okay. So one key observation from this is, like, one might ask, why do we alternate between these? What about those classes which have two same existential quantifier in succession? Like there exists, or it could be for all, right? So as it turns out, you can always uh, lapse two same quantifiers together. You can lapse two their existential quantifier into one without changing the problem. Same goes with universal quantifier as well. Lapse into universal quantifiers won't change the problem. But you cannot interchange these two, universal quantifier and for, you cannot interchange the order here. It will be a different problem. Yeah, so you can check out the proof in discrete maths, but you can just work out an example. There exists x for every y, likes of x comma y, where likes of x y comma y represents that x is liked by y. So these two will be different statements if you just change the order, right? You can work that out. Okay. So next observation we can follow is sigma I is a subset of sigma I plus 1. Okay. And product I is a subset of product of I plus 1. So this NP is contained in sigma 2 and sigma 2 is contained in sigma 3, right? Yeah, so on. Also we can follow that sigma I is also a subset of product of I plus 1, right? And product I is a summation subset of sigma I plus 1. Okay, these are the observations we can draw from this notation, from this part. Okay. Yes, now we can move on to, we can check here properties of an P as a sigma to P. If L belongs to NP, then L belongs to sigma to P. How do you prove this? And if L belongs to co-NP, then L belongs to sigma to P. Okay, we stated this earlier, but here we'll think about intuitively how we can prove this. So the definition of NP goes like this: X belongs to L if and only if there exists a U and Turing machine M such that M accepts. Where, as you can see, the definition of sigma to P is more generalized. There is one more quantifier for all V here, right? Such that M x comma U comma V. So you can show a construction of a Turing machine M dash, and simply just, the idea is to just ignore the second certificate. You just pass any certificate, and just in the Turing machine only you just said that um, you don't write the steps for V. Whatever happens to V, just always accept, like if U is accepting. The key idea is that you have to construct the machine M dash in the definition of this. So M dash is equal to M, ignores B, and simply work as before on U, right? So same goes for co-NP also, but in co-NP you ignore the first certificate. You ignore the first certificate. You have to construct the machine in this part only. You just ignore the first certificate. Okay, yeah. See, in co-NP you just ignore the first certificate, and to prove NP you just ignore the second certificate. So yeah, we stated this earlier. We are just generalizing the sigma to P to IX level. As I said, Start with the existential clause and keep alternating till the ith level to define the sigma I. So for every I greater than 1, a language L is in sigma I P if there exists a polynomial Turing machine M and a polynomial P such that X belongs to the language if and only if there exists U1, keep alternating till ith level, UI. So you define basically I certificates there, and the Turing machine accepts the input and I certificates and outputs 1. Okay, and yeah, all these certificates should be polynomial in the input. Okay, so we have defined I, and similarly we define product IP. Product I is subscript I or superscript P. Okay. Yeah. So now we define the more uh, superclass of all these sigma i's and product i's. That is our polynomial hierarchy. So PH is nothing but some union over all sigma i's and also union over all PLs. Should switch here. Yeah. So PH is union over all sigma i's and union over all product i's. So the problem is in PH if it can be expressed in terms of sigma i's or product I for some I. So this is the uh, hierarchy where a line indicates that is a subset. So P is a subset of NP. P is a subset of co-NP. Co-NP is a subset of product 2 and sigma 2. NP is a subset of phi 2. So we have written that this is sigma 1. This is sigma 1 and this is product 1. So yeah, as I said, product 1 is a subset of product 2 as also. Product 1 is a subset of sigma 2. This goes on, and PH is thus just a superclass of it. Okay. So yes, here we already defined it. So some immediate observation: sigma IP 1P is NP, sigma product 1P is 2NP, and these two are complement of each other. From the first observation, we can conclude that product IP is complement of some sigma IP. Okay. It should be 1 here. I think it should be 1 here. Well, it should be 1 here. I think it's a little mistake here. So it should consider this as 1. Okay. Sigma IP is subset of sigma I plus 1P. Same goes with the product also. I should write it here. Product IP is a subset of product I plus 1P. I don't have a touchpad. Yep. And yeah, this also follows the same as we discussed here. In this, from this, it follows directly, right? Yeah. Now we'll be discussing about. We'll be not proving it thoroughly, but we'll be just going through the proof on a higher level, how the proof follows. Okay. So first claim is that if P equals NP, then the polynomial class polynomial hierarchy equals P. Okay, so indirectly it means to say that the hierarchy collapses to P if your polynomial class is equal to NP. How do you prove this? So yeah. So first observation, what we can draw from P equal to NP, that if P equal to NP, then NP equals to co-NP equals to P. This is important. I think this has been proved in previously also, but Yeah, it is equal to co-NP. Okay. How we can say that NP equal to co-NP if P equals an NP? Yeah. So if P equals to NP, that means that all the problems that are quickly verifiable can also be decided very quickly. It can also be decided very quickly, right? So as our P problems are closed under complementation, that means NP is also closed under complementation, and which is NP complement is nothing but co-NP, right? So this directly follows that co-NP is equal to NP, which is equal to P. Okay, so I think we turn to this for example. Okay, so P equal NP implies PH equals NP, which is equal to P. PH equals to P, right? PH equals to P. So how do you prove that? We stated earlier that P is equal to NP, and NP is nothing but there exists with P, and P is nothing but co-NP, which is equal to for all P. At the second level, sigma 2 and pi 2, you can say that sigma 2 is equal to there exists for all P, right? You can say it on this slide. Sigma 2 is equal to there exists for all P, and for all P, as I said, for all P we can replace with here. For all P we can replace with P. For all P we replace with P, and there exists P is nothing but P. So sigma 2 is also P, and let me see, pi 2 or product 2 is also P, but from the same argument that there exists P is also same as P from here. So this is at the second level. At the third level, we'll use this result, okay? And so we prove for the base cases, and we introduce at the kth level, and finally prove at the k plus 1 level using kth level. So this is an easy proof using induction, okay? So you can work that out in assignment question maybe. Yeah, so yeah, yeah, this is also proof of induction here. We talk about proof of induction here. I'll just skip through the slides. Okay, and the next claim that we wish to prove is that at certain stage I, if sigma ip is equal to product ip, then all of the later stages, oops, then all of the later stages j greater than I, it collapses to that level. That is sigma jp if sigma j is equal to product j is equal to sigma. What it's trying to say is that here, if at a certain level, let's say this level, these two get equal, then everything beyond this or next to this or next to this, all of this will collapse to this level. Sigma 3 will be equal to sigma 4 is equal to sigma 5 is equal to product 3 is equal to product 4, and so on. There will be no level next to this. This will be the final one. Okay. So how do you prove this part? That if where's this? Yeah. So how do you prove that part? That if at ith level they become equal, pH will be equal to summation I. As it turns out, you can always use induction to prove it. For instance, take a level, the the very first level, the co-NP and NP one. Okay. So yeah, here.
So let's say co-np equals to np. Okay, that means there exists equal to p. There exists p equals to for all p. This is the first one. Or at the second level, we can say that this is nothing but sigma 2. Yeah, this is nothing but sigma 2, and this is nothing but pi 2. So sigma 2 is equal to there exists p, right? And pi 2 is nothing but for all p, which is nothing but are equal, right? Which is the very first level. So at the third level also I can show that there exists for all, there exists p is equal nothing is equal to there exists p, and as I said, two existential quantifiers can be lapsed to one, right? And same goes with the story of a universal quantifier, they can be lapsed to one, right? Yeah, this part and this part, they follow from the previous one. So it's nothing but summation, so we replace it with that. So same as we talked about the previous proof, we prove the first three base classes induced for the kth level, and then finally prove to the last k plus 1. Okay, all right. There is one such question. Yeah, let's see if we have anything from this, that another collapsing result. So we have till now, till this point, we have shown two collapsing results. First being, if np equals p is proved, we can show that the polynomial hierarchy collapses to the pth level, to the very base. It means it collapses to the p level. And what if some sigma is equal to p product I, then the polynomial hierarchy ends at that level. There is no further than that. All of the polynomial hierarchy beyond that collapses to that one. Okay. Yes. Okay. So this is the proof by induction, right? So I took an example and shown it, but you can also take any arbitrary level I and show it. Okay. So yeah. So there's one key observation that we can make. What if L belongs to the intersection between NP and co-NP, and L is NPC? What if the intersection between NP and co-NP is NPC? We can and we can show that it means that NP is equal to PH. The whole polynomial hierarchy collapses to NP. How we show that? We just need to prove that NP is equal to co-NP. And from our previous argument, that when we showed that NP is equal to co-NP, we proved that PH is equal to NP. And it's a relatively simple proof to show that NP is equal to co-NP if the intersection between them is NPC. So we basically show that if this is a subset of this and this is a subset of this, and this, first we need to show that NP is a subset of co-NP. The way we show this is we take an arbitrary k which belongs to NP and show reduction between k to L. And as you know that L is in co-NP, so k is also in co-NP. So NP becomes a subset of co-NP. Same follows the suit from for co-NP also, proving that co-NP is subset of NP. Alright, we finally go to complete problems. So as we said, we had NP complete problems. So what about the sigma I complete classes? For each level, as it turns out, we have a complete problem. We can define for complete problems, though I don't think we can define more practical problems beyond sigma 3 4. But yeah, in general, we can always theoretically we can always define our sigma complete problems. Okay.
So what about the complete problems for each level of the hierarchy? So in we take the SAT example here. Okay. So for NP complete problems, there exists a certificate U that Boolean phi is satisfied with, right? So similarly, we define here sigma I SAT. Okay, sigma I SAT is nothing. It's alternating quantifiers here, and phi U1, U2, Ui. So basically, each of
This UI is a sequence of Boolean variables of size n. Okay, each of them is, and you basically have to satisfy all of them simultaneously. That's the sigma I SAT problem. Okay, so one exercise could be to prove that sigma I SAT is sigma I complete, and another could be sigma I SAT is product I complete. Yeah, these two could be a good exercise questions. Okay, so yeah, that's pretty much all. We'll end here. In the next lecture, we'll discuss about Oracle machine and describe how sigma IP can be defined in terms of Oracle turing machine, and then we'll see alternating turing machine. Okay. Yeah, before leaving, this is the final polynomial hierarchy we get after discussing this. There is NP class, there is co-NP and NP overlapping P. There is summation 2P, which has NP and co-NP as well. Product 2P, which has NP and co-NP. And beyond all these sigma IPs, intermediately there will be, right? There will be many more classes in between. And there is PH. And what about the upper bound on PH? There is upper bound on PH, we can say there is P space. Okay.